In the earlier class, we saw about the rectilinear motion, right? There's a motion along the straight line, and we saw then we defined the quantities: velocity, acceleration, average velocity, instantaneous velocity, means acceleration. Okay, we saw instantaneous acceleration. We did all those things. Okay. So now, but in if there is a body which is moving in a plane, that means what? It may not be a straight line. It may have a different, means not a straight line. So it is on a plane. It is moving. Suppose a ant is moving, or a car is moving on the road. It's not going to be a straight line. Okay. So in that case, how are we going to define these quantities? Okay, and that's for the real thing, because though we are living in a 3 dimension, most of our motions are confined in a plane. Okay, for example, if you will study later on the projectile. Okay, spin a stone on a rope and spin it. It will be in a circle, right? The circle is on a plane. So most of the cases, these motions are in a plane, 2 dimension. So then in that case, how are we going to do these quantities? And plotting a graphical representation of a motion in 2 dimension cannot be dealt in the same way as we did in the 1 dimension. Why? If you remember, in the 1 dimension, what we did, when we were dealing the velocity, what we did, we plotted x here and time here, right? And then we did those things. So we took only one x because it's a rectilinear motion. Now it's not going to be only x, it's going to be x and y. So we can't do that. Similarly, we did for the velocity also. Remember? We took the velocity and time here, then we defined the acceleration. Okay, so these things won't work in a 2 dimension. That's in a plane. So we have to do a different type of plots, graphs. Okay, I will see how to do it out. So in a 2 dimension, so what happens? So let me say, so if there is so in a 2 dimension, what happened? Let me call this as your x, correct? X-axis, and this is your y-axis, correct? So then we can define some trajectory. Trajectory means it's a trajectory of a body. Okay, some body is moving, some particle is moving. So what happens? So let us say, let it move from here to here, something like this. Okay, and when the body is here, it's a 2 dimension. It's not a rectilinear motion. You got it? Na? It's not a straight line. So when the body here, let the time be, say something around t1. The body is here, and when it is here, this is t2. So now we have to define the average velocity, instantaneous velocity, average acceleration, instantaneous acceleration. All those things we have to define for the motion in a plane. Okay. So how are we going to do that? So before we going to do that, what we have to see is there's something called as important quantity, which we call it, because now these are all vector notations, right? Because these are having a direction. X, there will be any vector if you draw in an axis. You remember we last time that can be resolved into x component and the y component, and then we write like, okay. So now we are going to really deal with the vector, the motion in a plane. Okay. So there's one important quantity, what we call as a position vector. What do you mean by position vector is, you fix up certain origin. You are sitting at a certain place. I am standing in a certain place. So from the origin, you are occupying a definite place, right? At a certain direction from the origin you are sitting. And I am sitting at a certain other direction of a fixed magnitude. Okay, so this vector, what is called as your position vector. So let me say, let there be a point, let there be one point, maybe whoever, it may be you or whatever it is. Okay, so there's a point there. So let it be x1, y1. Then then this point will have a position. This is the origin, am I right? So what you do is you join this point and this vector is called as so let us call it as R1. Okay, what is that? R1 is position vector. This is a vector. Okay. So now, now say there is a body which is sitting at a certain position. So this is x1. After a certain time, maybe during a time t1 it is sitting here. Let me write it bigger. t1 it is here. After a certain time, this body has moved to some other point. What happened? So let this be x2, y2. So now this is a new position vector. Am I right? So then the body's new position vector is, so this is the new position vector. Let me call it as R2. Okay. So now you know what is your R1. We can resolve R1 vector. Correct? What is R1 vector? Tell me. If this is x1, y1, what is this direction here? I cap. Am I right? This is j cap. So this will be what?
x1
I cap plus
y1 j cap.
And similarly, R2 will be
x2 y cap
x2 y I cap
plus y2 y cap.
y2 j cap.
Oh, j cap, sorry.
Okay, so this is the way we resolved. Now, so what happened? This was the initial position. And this is the final position. What is the displacement? Can you tell me what is the displacement?
You need to take the shortest distance.
This is the distance, right? So this is the displacement. Okay. This is the displacement. Let me call, so the body has moved from here. Let me call the displacement as delta R. Okay, this is also a vector. Am I right? This is the direction it has moved. Am I right? So now you have to tell me what is your delta R. Given these two position vectors, what will be the delta R? That's a resultant vector, right? What you can do? We have to use the vector addition. Am I right? So what it will be delta R?
Delta equal to R.
Tell me. You have to take the proper direction.
Minus R1.
Yes, exactly. R2 vector minus R1 vector. Am I right? Why it is? Because the opposite direction. Remember in the vector addition of law, what we do is, suppose you have a, how do you do? You have the A vector and B vector. So this will be the opposite sense, right? That is C vector. So this was C vector equal to A vector plus B vector. So this serves to the same direction. Now, but here you see, these both are opposite. So you can see for the direction itself. So R1 vector plus delta R vector will be equal to R2 vector. So delta R vector will be equal to R2 vector minus R1 vector. You got it? So that's all. Fine. Okay, so now we got R1 delta R vector equal to R2 vector into R1 vector. R2 vector minus R1 vector. So can you resolve this also into two components? How? Tell me. So this will be what? Simple, you take it. Na? R2 vector, write R2 vector. What is R2 vector? x2 I cap plus y2 j cap minus x1 I cap minus y1 j cap. Now you can't combine j and I and all. Okay, you have to combine only I caps, the direction along the ith vector. So this will be what? x2 minus x1 I cap plus
y2 minus y1 I cap
j cap. Okay, so this is way to solving the vector also. Now tell me. So now this is the displacement. Okay, so your actual displacement, the particle, this is a displacement. The particle wouldn't have traveled like this. Now the body may have traveled something like this. These are two times. Okay. So then what happened? The time will be what? Let me call the time taken. That will be what? Suppose if this is T2 and this is T1, let me write here. This is a T2, it is here. So delta T is T2 minus T1. Now you can define an average velocity. What will be average velocity? Tell me. V average will be delta r, right? This is a displacement between two times, right? Delta r divided by delta t.
Delta t.
Correct? So that will be what? Delta r equal to what? R2 vector minus R1 vector divided by delta t.
T2
T2 by T2 minus T1. T2 minus T1. Okay. So otherwise, so if I want to R2 minus this vector, I can resolve it like this also. Correct? So your average vector will be
x2 minus
x2 minus x1
divided by
T2 minus T1 I cap plus y2 minus y1 divided by
T2 minus T1
T1 j cap. Okay? So this is how your average velocity can be written. Okay? So we can, in fact, we can write this as, so now you tell me, so this is x2 minus x1 by T2 minus T1. What is that? That is x2. Okay, let me drop this line perpendicular here. This is x2. This is x1. Okay, so if you see here, x2 minus x1 by t1, x2 minus x1 by t1, this is something like a rectilinear motion, right? So this is nothing but, your V average, I wouldn't say what they written the symbol is here, VAVX. Okay, let me write it as VA average along the x component. Am I right? Into I cap. Similarly, this one. So what is this? This is y2 and this is y1. So if you see, this is something at the, if you take those one at here, at t1 it was here and t2 it has reached here. Correct? So then y2 minus y1 by t2 minus t1 is nothing but it's also velocity, average velocity. It again can be treated as a rectilinear. You got, because along the y-axis only, rectilinear velocity. So that is a yth component. So this will be what? So your V average of y component into j cap. Okay. And now, so what it means? So if you actually see it carefully, that means I can, the same way in the earlier rectilinear motion, we plotted x and y, and next for acceleration we plotted v and t, correct? So then I know VAV x is also there, VAV y is also there, correct? So then you can again resolve in the place of x and y, you can write Vx, Vy, okay? So Vx and Vy, and then this vector VAVE, we can write it as a certain vector. This is VAVE, am I right? Can we write like this? Which can be resolved into two component, and this distance is what? VAVE x component, and this will be E y component, or rather this point is what? VAVE x comma VAVE y. Okay. So now tell me what is the magnitude of this vector? That's the length of this vector, correct? What will be the length, you tell me?
VAV.
Magnitude of VAVE will be what? What's the length of this? This square height.
Root of V average component of V average x component whole square.
Okay.
X component square plus V average y component square.
Okay. Or in general, if I don't write VAVE, I can even write it as any vector So any velocity vector, let me call it as V, can be resolved into Vx, Vy, okay? So this is Vx, this is Vy. In that case, the magnitude of any of this vector, where will I write? Okay, for this vector, V will be what? Tell me, square root of?
Square root of Vx whole square plus Vy whole square.
Okay. Can you tell me what is this angle? Tan theta. Simply tell na. Tan theta equal to what?
Tan theta will be equal to Vy by Vx.
That's it. You already read na in this. Okay, so that is the angle because so this together defines your vector. Remember, this vector should have a magnitude as well as a direction. Theta gives you the direction. Okay, so this is how average velocity is defined in a plane, for a motion for a body in a plane. Okay, now we can define, once you define the average velocity in a plane, we can define this average velocity in instantaneous velocity also for motion. How will you do it? You remember, instantaneous velocity will be the same thing, only delta t should goes to 0. Am I right? Because this is 1. That is, when the delta t becomes 0, take it as a certain point, draw a tangent. Am I right? Something like that we did earlier. So when we get a tangent, no, not here, not tangent, that time we go to, the time is on the x-axis. I am saying in the rectilinear motion, what we did is, when the delta t becomes 0, then it becomes the instantaneous velocity. Okay. So similarly, from here, then I can write the instantaneous velocity as, what is that? Instantaneous velocity. So what is the symbol they have? Okay, the symbol they are just V. Okay. V will be equal to limit delta t tends to 0 delta r by delta t. Okay. Now you can see, yeah, actually we can write this as, see this one what happened? This we can write it as delta x by delta t times I cap plus delta y by delta t of j cap. Am I right? So then if I write like this, so this will become what? Limit. So this is a vector. Remember, I am going to resolve it into the components. So delta t goes to 0. So this will be what? So delta r by delta t can be written like that, right? So this will be what? Delta x by delta t I cap plus delta y by delta t j cap. And if I open it up, so it means when delta t becomes 0, this is going to become dx by dt. This will become dy by dt. And this will be dr by dt. Am I right?
That's
so
only it should be delta t, right?
Which one? This one?
Limit. Below the limit.
Oh, no. This one. Delta t. When delta t goes to 0. Okay, it's not time going to 0. Delta t. The difference in time goes to 0. Okay, so this will be what? Tell me. dx by dt I cap plus dy by dt j cap. You should remember. Okay, this delta t. So time gap. That's why earlier also we did some mistake there, right? So you should remember this. Go and read it properly. That one. Huh? So, or we can write this as your, this is what you call as Vx I cap plus Vy j cap. Okay, this is the way we can resolve it. And that's what. And now here also again you can see. Okay, so this is again instantaneous velocity. And here your, what will be your magnitude? Tell me. Magnitude of the instantaneous velocity vector will be the same thing, Vx square. Okay, or if you want to write, the magnitude of v instantaneous velocity will be root of dx by dt whole square plus dy by dt whole square. And the angle tan theta will be dy by dt divided by dx, rather I would say dx by dt, or if you want to write it,
dt will get cancelled.
correct,
So dy by dx.
correct, exactly, dy by dx, correct. Good. So this is what your thing about your instantaneous velocity in a two dimension, or the motion in a plane. Okay, two dimensional motion. In your book, instead of r, they have used x, and for this also they have used x. Okay, so x1, x1, so it was confusing. That's why I changed it to r. Okay, so whatever the way you can use it. Okay. The same way we define the instantaneous and average velocity for the motion in a plane and in two dimension, we can define the instantaneous and the average acceleration also. You remember the rectilinear motion, what we did? We plotted x versus time. Am I right? And then we plotted, got the velocity and all. When you want to get into acceleration, what we did? We plotted velocity and time. Correct? Same way we do it out here. So what we are going to do? Earlier we plotted x versus y. Correct? Now I am going to resolve it into velocities, two velocities. You got it? So let it be Vx and Vy. Okay. So and then we have means, yeah, okay. So then let me define a velocity, certain velocity, certain point. So let this be, there's a velocity v1. Okay, I am defining a velocity v1 vector, and then another velocity v2 vector. Okay, so then what happens? Then you cannot define. Okay, what's the, if at time t1 the velocity is v1, at time t2 the velocity is v2. Okay, then you can join also this, whatever you can do it out. Okay, so and I remember v1 vector will be what? Will be equal to, tell me, vx1 I cap. I'm going to resolve. Am I right? If I resolve it like this, I can write it as vx1 and vx2. Sorry, vy1. y1. Similarly, this I can resolve it as vy1.
x2.
Oops, sorry. Yeah. vx2 into vy2. Okay, so vx1 I cap plus vy1 j cap. So similarly, v2 vector will be equal to vx2 I cap plus vy2 j cap. Okay, so now we can see the same thing. So if you want to go for an average acceleration, so what is the symbol they have? AV. Okay, the acceleration will be what? v2 vector minus v1 vector divided by t2 minus t1. The same way what we did. Okay, so if you want to resolve it into components, then what it will be?
vx1
Correct.
vx2.
Correct. They have written the same thing. So what is that? No. Yeah. Okay. This will be what?
vx1
vx1 I cap plus, no, v2 this is.
oh vx2
vx2 I cap plus
vy2
vy2, oh, y2 j cap minus
vx1 I cap
plus
vy1 j cap
divided by t2 minus t1. So we can write it out. So what is that? vx2 minus vx1 divided by t2 minus t1 I cap, good, plus minus
Vy2 minus Vx
y2 minus vy1
divided by T2 minus T1.
into j cap. Okay, got it? So this is the average acceleration which can be resolved it into two components. And again the same thing. This you can write it as again the same way what we did. This can be written as AAV of x component I cap plus AAV of y component along j cap. Okay, and that's what they have written. And therefore the magnitude will be what? Tell me. Magnitude of the A average vector will be what? Square root of this square plus this square. Correct?
A average x component square plus A average y component square.
And what will be the angle?
Should be tan theta is equals to A x1 by y1 by x1 y by x.
Just plot now. What is that? Your acceleration. Na? You write it as AX, AY. Acceleration, you do it. Okay, so this is an acceleration. A. Okay, so this is what? AY. This is X. So theta equal to what?
AY by x.
Correct. So it's what? AAV of y component divided by AAV of x component. Okay. So always whenever we take the angle, plot that vector. This is a vector, na? Plot this vector, resolve it into two components, take the angle. That's what. Okay. So this is how. Okay. In the same way, we can define your instantaneous acceleration also. Correct. So what will be instantaneous acceleration? Tell me. It's one and the same. The same way we can do it, na? So okay, well, I removed it. So okay, yeah. This, if you remember, what we wrote is AAV, right? That is equal to what we did is delta V vector by delta T. Am I right? And this we wrote it as
V2 minus V1.
V2 vector minus V1 vector divided by delta T2 minus T1. Correct? See the same thing. I remember what I am saying. I have not drawn the line. This is a V1 vector. This is a V2 vector. So this will be a V2. Change in time. That one. Okay. So the same thing I was doing here. So what I did the earlier one, the same thing I am doing here. Don't get confused. So then for instantaneous, what happened? A, that's a vector will be equal to the same thing. Your T should, delta T should become 0. So limit delta T tends to 0, del V vector by del T vector. Am I right? So what will happen? Tell me now. Yeah, okay. What they have written is, so this will be, this is what we call as your dV vector by dt. Am I right? This again you can resolve also. You remember that? How do you resolve it?
dV vector from the.
So this will be dvx, dvx dt by I cap plus dvy by dt j cap. Am I right? Well, basically that's how you resolve. The same thing I am going on. Okay, so and now actually in fact you can do one step further also. What is Vx? You remember? In the earlier version, Vx is what?
Vx is dx by dt. We can substitute that.
Correct. And similarly, Vy will be equal to what?
dy by dt.
Dy by dt. We just saw before, na? So when you substitute, what happens? This will be called a second derivative. D by dt of dx by dt. Am I right? I cap plus d by dt of dy by dt j cap. Okay, and what the way they write it is, this is written as d square x by dt square I cap plus d square y by dt square j cap. Remember, this is just a symbol. It's a double derivative they call. Don't think this is a square times square, or so you can't do that. Okay, so this is just a time derivative. Okay, and that's what they have written here. So, okay, this is what we write it now. So, this will be what? If you want to write one more step further, so this will be what? This will be your, this is a AX I cap plus AY J cap. Am I right? So, AX is what? So, if you write, so AX will be what? This is what is the acceleration, no? Because that's what you written, right? Okay, so, oops. Right. Correct. This is acceleration. Along this is being resolved into I and j component. Am I right? So AX is what? D square x by dt square, and I cap nahi, AX I'm asking na, to d square y by dt square. Okay. So AX is what? Acceleration along the x-axis. AY is the acceleration along the y-axis. Once you resolve it, they become a rectilinear motion. That's why whatever study rectilinear motion is important, because once you resolve, when you consider only the x direction, then you can treat the whole thing as a rectilinear motion. When you resolve it to the y component, then when you deal only with the y-axis, that becomes a that's also again you can delta as a rectilinear. When you can combine them with the proper unit vectors, then it becomes your actual two dimensions motion in a plane. Okay, and yeah, there they have given, okay, the same way from there you can write this also. So the magnitude can be written like this also.
Root of AX.
Dx square d square x by dt square whole square plus d square y by dt square whole square. Got it? And then the angle also you can write. The angle, if you remember, what do you remember? Tan theta AY divided by AX. Am I right? AY divided by AX. That's what we did, right? AX. So that will be AY equal to what? dy by dvy. Sorry. This will be what? dvx by dt. Am I right? This will be dvy by reverse. No, I'm writing in velocity. d vy. Yeah, if I write square, then it will become d square x. I'll show you. That's what you have the mistake. You shouldn't do it. dx by dt, dvy by dt divided by dvx by dt.
dvy by dt.
Correct. This will be what? dvy by dt. Remember, dvx. Remember one mistake. See this, why I said that you can't simply strike off and cancel this derivative is, last time I was telling that. The reason is here comes here. So now you can't write this as, so if you can't write this tan theta as, so I can write this as d square y by dt square, correct? So d square y by dt square divided by d square x by dt square. Okay, you can't cancel dt square and write as d square y by d square x. This is meaningless. Okay, there's nothing like that. Okay, so that's what. In a derivative, you can't simply cancel the terms. In this case, you can do it. Okay, so this is not the right way of doing. You shouldn't do this way. Okay. When it comes second derivative, you should be very cautious. Acha, there are also one more, which is a slope. The tan theta is a slope of the tangent to the curve in the velocity graph. Correct. Yeah, this is dv by dx, na? This is what? So in the velocity curve, that's a slope. Am I right? This is a dv by dx. The same way there also we can do. Tan theta is a tangent of the slope in the two-dimensional curve. Okay? After defining this quantity, we can do the equations of motion like we did for the rectilinear motion. Okay, in your book they have done a way, but that is not the exact right way of doing. How do you get the how do you get the equation of motion is resolve all the quantity in the x component, y component. And there, in the x component, everything is a rectilinear motion. Am I right? So when I deal only with the x component, that's a rectilinear motion. Whatever the equation of motion you derived earlier, that can be used there. Similarly, when you do for y component, that's a rectilinear motion. You can do the thing. And then when you want to get a particular component, you have to take the combination with your cap, with the unit vector. Okay, I will give you some examples of that. Okay, anyway, first I will do what the way they have done is, okay, so what they have done is to get the equation of motion. The first equation of motion, what they have done is, suppose you have a acceleration is what? Change in velocity with respect to time. Am I right? So that's what we did. So you have suppose for example, there are two velocities. I will give initial velocity is u and the final velocity is u, final velocity is v. Let this be at 0 time. At t equal to 0, this is the velocity. At t equal to say certain time, so is velocity. So then what is your acceleration? A is equal to v minus, this is change in velocity, am I right? Divided by t minus 0, that is equal to v vector minus u vector divided by t, okay? From here what happened, your v vector will be equal to u vector plus at. A is a vector. The same thing what we got earlier. Here also all the equations of motion what you derived in your rectilinear motion will be same in the two dimension also, or the equation plane motion in the plane also. Only those quantities will be replaced by your vector notation. Okay, and then they have done another one also. Your in your book, the second equation they given as, this is not, you can write it out. So suppose for example, this is the velocity. Initial velocity is u and the final velocity is v after time t. So then you can define an average velocity, VAVE. So average of a two number. Do you remember in your mathematics when you do average of a two numbers? What is that? If I give average of 1 and 2, can you tell me what is average of 1 and 2? 1 plus 2 divided by 2, that's equal to 1.5. Right? So similarly, take the average velocity, what happened? U vector plus V vector divided by T. 2. Divided by 2. Okay, and then so this is average velocity. Okay, so that means, if you remember, that is a average velocity gives you the displacement by time. Am I right? So let me call the displacement as S by time t, and this is your average velocity. Am I right? So then what they written? So this here. So from here you can write S vector will be equal to VAVE into T. Am I right? What is VAVE? U vector plus V vector by 2 into T. So now let us write, in the place of V, we will write this. So then what happened? U vector plus V equal to U plus AT by 2 into T. Am I right? So this will be equal to
2u vector by 2, that will be u vector.
Yeah, U vector
Plus half AT square.
Is that your formula? So S is equal to UT is there. UT is there. Am I right? So yeah, this T is there, na? Okay. So let us write it neatly. So your S vector equal to U vector T UT plus half A vector T square. Okay. This is a book done, but actually you shouldn't, the right way of doing is to resolve it into two components. That's what we studied about resolving a two vectors. Okay, so what you can do is once you resolve, then you can use all the same components. So you remember what are the equations we had earlier? Equation of motion? V equal to U plus AT, and then S is equal to UT plus half AT square. A third equation, I'm leaving the third equation. We don't want to write. Yeah, that's combining these two. If you remove the t term, that will come up. Okay. So, so here, so the moment, this is for the rectilinear motion. Okay. So when you want to do it for a 2 dimension, resolve everything into x and y component. So then what happens? So if your Vx will be ux plus ax t. Vy will be uy plus ay t. That's what. You are resolving these vectors. Am I right? So this is the x component vector. This is a y component vector. Okay, so you had certain u. Am I right? This is a u vector and this is the v vector. Resolve this. So this is what? This is a ux, uy, vx, sorry. This is a vx. Am I right? So deal this is a rectilinear motion. So that's what we got this here. This is acceleration, right? So this is what we have done. It's a rectilinear motion.
But even after resolving them in two different, from x-axis and y-axis, how will you take it in the plane?
Correct.
How will you combine both of them?
Correct. So your velocity, the final velocity. So now I am giving you initial velocity u vector, and I am giving you your acceleration. Resolve it into 2 components, ux, uy. Am I right? And resolve this into 2 components, ax, ay. And I ask you what is the final velocity after a certain time t. Say let us say time duration t. What you do? Use this formula. So Vx is equal to ux plus axt, and Vy will be uy plus ayt. Therefore, your Vx I cap plus Vy j cap. You got it?
Okay.
You got the vector? You got the component. That's all you have to do it. Correct? So this is how the vector is being defined. Okay, the same way, go for the second law. What does that? S is equal to, same thing I can do. S of x equal to uxt plus half axt square. And S of y will be equal to uyt plus half ayt square. So your displacement S vector will be equal to sx I cap plus sy j cap. See, it's simple. Whatever the moment when you resolve it into x-axis, they are rectilinear motion, and this is a rectilinear motion. Okay, so you can deal with all the equations of rectilinear motion, and just when you want to get back the vector, combine them and put the proper unit vector. Got it? So this is how your equations of motions can be attained for a object traveling in a plane. Well, remember, this is for uniform acceleration. We are dealing only for the case of, even there also, the motions are defined for uniform acceleration. Okay, so and that's all. So I will stop here. Tomorrow we will see about another one, relative velocity in case of motion in a plane, and then we will see an interesting topic, that is the projectile motion. That's projectile motion when you throw a stone.
There's a question. Throwing the stone from a moving bus.
Moving bus is that's the one part. Just even if you stand, can you, when you throw a stone, you give the initial velocity and all, can you trace back the stone where it will fall? Okay?